Okay, so we started looking at this problem yesterday in class, and I figured make a quick video, give you a couple to try with some solutions, and then we can talk more about it next week if we really need to, because it is just an extension of the numeric versions that we did do in class and that you did last night for homework. So we want to write the sine of cosine inverse x plus tangent inverse y as an algebraic expression in x and y, which means we want no trig functions involved. We just want x's, y's, and operations if need be. Keeping in mind that cosine inverse x is really representative of an angle, and tangent inverse y is representative of an angle. So this really says the sine of alpha plus beta. This is a sum formula task. So we start by identifying what those angles are, because if we're going to use the sum formula for sine, we're going to need to know the sine of the first and cosine of the first, and the sine of the second and cosine of the second. And so we start to build those out. If cosine inverse x is alpha, that means cosine alpha is x. It's a good start. It's one of the things we need. And if tangent inverse y is going to be equal to our beta, then that means tangent beta is y. That doesn't directly give us what we want. We're going to have to work for it a little bit. Starting with the alpha, we need sine alpha. Well, our Pythagorean identity, as long as we're staying inside of our boundaries, right? X has to be between -1 and 1, and for tangent, y could really be anything. Our Pythagorean identity says that sine alpha is the square root of 1 minus cosine squared alpha, manipulated so that it's solved for sine. We know that we've got a representation here that's going to be legitimate. We've proven this over and over and over again and used it a ton of times. So that means sine alpha is the root 1 minus x squared. For tangent, we have to build out that triangle because we don't have a direct correlation we can work with. So we take the triangle, and tangent being opposite over adjacent, so y is the height of our triangle, and 1, y over 1, so 1 is the initial side of that angle that we're working with. And using the Pythagorean theorem, that means that the hypotenuse is root 1 plus y squared. So now we can build sine and cosine from that. Cosine beta is 1 over root 1 plus y squared, and sine beta is y over root 1 plus y squared. Now it's just about putting those pieces in place. We've got sine alpha plus beta equal to sine of the first, cosine of the second, plus cosine of the first, sine of the second. And then we start replacing all those values that we just found. Algebraically, once we've condensed this, there's no more sines and cosines in the representation for the expression. We'll have achieved our goal. So that means that sine of cosine inverse x plus tangent inverse y is root 1 minus x squared plus xy over the square root of 1 plus y squared. Now, that is fine as an expression. I know there's a radical in that denominator. I know it. It's there. We're going to leave it. If you'd like to go through the task of figuring it out, by all means, take a shot at it. In terms of having achieved our goal, which was represent it with just x's and y's, we got there. So, new task. Sine of sine inverse x plus cosine inverse y as an algebraic expression in x and y. I want you to pause the video. I want you to take a second, and I want you to work this out, and then you can come back and look at the solution. We're going to have 2 here for you to do, so take a second and pause. All right, so here is the solution. We start by building out sine and cosine of each of our 2 angles, what we're going to call alpha and beta. Sine inverse x, that's going to be equal to alpha. So sine alpha is equal to x as long as x is between -1 and 1. Cosine inverse y, that's equal to our beta. So cosine beta equals y, where y is going to be between -1 and 1. Just reminding ourselves the way that those inverse functions work. Using the Pythagorean identity, we can find cosine alpha equal to root 1 minus x squared, and sine beta, root 1 minus y squared. And then we go to our formula. Sine alpha plus beta, sine of the first, cosine of the second, plus cosine of the first, sine of the second. And we replace with those things that we just discovered. All said and done, xy plus root 1 minus x squared times root 1 minus y squared. We're going to stop there. It only gets super ugly from that point on. This is enough. Cosine of tan inverse x plus sine inverse y. So now we've switched to the cosine sum formula, and we're going to bring that tangent back in for good practice, right? Because it isn't achieved through the identities. It's done working back towards that unit circle relationship that we built everything on. Take a second, pause here, and come back for the solution. So building out those angles. If tan inverse x is equal to alpha, that means tangent alpha is equal to x, where x is any real number. And if sine inverse y is equal to beta, that means sine beta equals y, where y is between -1 and 1. For tangent, we have to build out the triangle. We have to go back to that unit circle approach to looking at this. If tan alpha is x, that means x is the opposite side and 1 is the adjacent side. Using the Pythagorean theorem, we get root 1 plus x squared for our hypotenuse. Cosine, adjacent over hypotenuse. Sine, opposite over hypotenuse. 1 over root 1 plus x squared, x over root 1 plus x squared. Working with beta. With beta, we can use our identity. So cosine beta is root 1 minus sine squared beta. Cosine beta is the square root of 1 minus y squared. Now we go to our formula. Cosine of a sum is cosine of the first, cosine of the second, minus sine of the first, sine of the second. Replace with our algebraic expressions. Condense what we can. Again, we'll stop there. We achieved our goal. It's all x's and y's. There is some legitimate hairiness involved if we choose to get rid of that radical in the denominator. In this case, again, we're going to throw etiquette out the window and say the solution is there, we found it. No one's trying to divide this with a slide rule, promise.